In this example, we're going to sketch the graph of f of x. Now, it's much easier to sketch this graph if I write this over a common denominator. And so I'm going to do that first. My common denominator is x. And so in my numerator, I'm going to have x squared plus 1. From this, I can straight away see that there must be a vertical asymptote because x may not be equal to 0. So the vertical asymptote that I'm going to find is when x is equal to 0. The next thing I'm going to notice that in my function, it is an improper function because the degree of x is greater in the numerator than in the denominator. In other words, I must be able to find an oblique asymptote, and I'm going to do this using long division. Remember that when you write out your dividend, it must be in a reducing degree of x. As the x term is missing, I'm going to fill it in. So in my dividend, I'm going to have x squared plus 0 times x plus 1. In the divisor, I just have x. X goes into x squared x times, and x times x is x squared. When I subtract these, I get 0. Then when I bring down 0 times x, that is 0. So in fact, the next number that I have to bring down is 1. Now x cannot go into 1 without a remainder. That means that I have already found the oblique asymptote. The oblique asymptote is going to be when y is equal to x. As there's no x in my remainder, I will not cut my oblique asymptote. Now that I've found my oblique asymptote and my vertical asymptote, I'm going to move on to try and find my stationary points. To find the stationary point, I need to use the quotient rule for differentiation. When I find the derivative, it is going to be f prime x. I find the derivative of the top function, and that's going to be 2x. And I times that by the bottom function, which is x, minus the derivative of the bottom function, all times by the top function as it was. And that must be divided by the bottom function all squared. So I divide that by x squared. When I simplify this, I find that the derivative of the function x is going to be 2x squared minus x squared. So that's going to be x squared minus 1, and that's all over x squared. If I want to find my stationary points, I must make the derivative equal to 0. In other words, I'm going to make x squared minus 1 all over x squared equals 0. When I solve this equation, I have x squared minus 1 is equal to 0. In other words, x could have been plus 1 or minus 1. Now that I have the two x coordinates for the stationary points, I want to check, are they going to be local minimum or local maximum turning points? In order to do this, I need to find the second derivative. Finding the second derivative, which is the derivative of the derivative, I find that I'm going to get that it's going to be 2x all times by x squared minus 2x all times by x squared minus 1, and that is all over x to the 4. Now remember, you had two values for x. If your x is equal to 1, what are you going to get? Are you going to get a plus answer or a minus answer? When you substitute when x is equal to 1 into this expression, you will find that you are going to get a minus answer. Sorry, I meant a plus answer, because your second derivative comes out to be equal to the answer of 1. If my second derivative is plus, it means that I'm going to have a local minimum turning point. Now you have to do this again, and you're going to substitute when x is going to be equal to minus 1. And this time, when you find your second derivative, when x is minus 1, your answer is going to come out as a negative answer. In other words, you're going to have a local maximum turning point. Instead of doing the second derivative test to find whether it's a local maximum or a local minimum, you could have taken that x coordinate from the stationary point, and you could have substituted a value just smaller or just bigger than it to see what would you have found the gradient to be. Now we know that one of our x values, for example, was when x was 1. If I choose a number just smaller than that, obviously it couldn't be 0 because I had an asymptote there. Let's choose when x is a half, and then a number just greater than that, and I'm going to choose a value of 2. Put this value when x is a half into your first derivative, and you should find that you're going to get a negative answer. In other words, you're going to have a decreasing gradient to the left of that stationary point when x was 1. Now put 2 into your first derivative, and you're going to get a positive answer. In other words, to the right of that stationary point, your gradient is going to turn and become increasing. You can do exactly the same when x is minus 1. Choosing a number just smaller than that, choose minus 2. Or a number just bigger than it, but not as big as 0, so choose minus a half. And then you will see to the left of minus 1, your gradient is increasing, and to the right of minus 1, your gradient then becomes decreasing. Then lastly, I just want to check and see, is there going to be a y-intercept or x-intercepts for this particular function? Well, for a y-intercept, I must make x is equal to 0. Well, that is already, we know, going to be an asymptote. So therefore, there is no y-intercept. For an x-intercept, I must make y equal to 0. In other words, I'm going to have 0 is equal to x squared plus 1. But when I take that plus 1 across, you find that you're going to get imaginary solutions. In other words, there are no x-intercepts. I'm now ready to take all this information and to plot it so that I can find the shape of my curve. Remember, the first two things that you want to do are to plot your asymptotes. I've already shown you your oblique asymptote, and then in addition to that, you're going to have a vertical asymptote when x is 0. Then the next thing that you have to do is you have to put in the points where you had your turning points. We had a stationary point when x was minus 1, and we had a stationary point when x was 1. We said that our graph would have a local maximum when x was minus 1 and a local minimum when x is 1. And you can see that now my shape of my curve can be well represented. It's increasing to the left of x is minus 1, and then it decreases up until and tending towards when x is 0. Then after when x is 0, on the positive x-axis, my graph is decreasing up until the stationary point when x is 1, and then it increases again.